So it's a pleasure to have Cenke Xu from University of California, Santa Barbara. And he will tell us about experimental platform for phases with fractal and other subsystem symmetries. So please, Cenke, take it away.
Okay. Yeah, I want to thank the organizers for organizing this very exciting program. Although I cannot be there in person, well, I really want to be there. Florence is one of my favorite cities in the whole world. Well, I mean, so I will talk about experimental platforms or potential experimental platforms for systems with a fractal structure and fractal symmetries. So let me first introduce my collaborators. Nayan is my new graduate student, and Stephen Yan is a student of David Weld. David Weld is a Cold Atom experimentalist in our department. So this work actually, well, sorry, the first half of the talk is based on a work which is a joint force between our group and also the Cold Atom experimental group in my department. Okay, so I will first give a quick review about fractal symmetry and also other subsystem symmetry, and also I will talk about a order which actually is a spontaneous symmetry breaking of fractal symmetry. So in my talk, I will define this spontaneous symmetry breaking of a fractal symmetry as a fractal order. So please be please note that this fractal order definition is slightly different from what people usually mean by fracton state. So when people say fracton state, they usually mean fracton topological order. So here I just mean it's the fractal order is a spontaneous symmetry breaking of a fractal subsystem symmetry. I will get back to this point later as well. Then I will give a quick review about the experimental platform. It's called Reedberg Atoms. The Reedberg Atoms actually is a new emerging field in atomic physics. It's being used to simulate many strongly correlated condensed matter system as well. So in this talk, I will try to propose how to use the Reedberg atom to realize systems with fractal orders. Yeah, so I will talk about how to realize fractal symmetry in a fractal order, and also I will also talk about some other subsystem symmetry and their realizations as well. So this is the reference. Okay. So fractal. Well, I mean, fractal, we know that it's a class of geometric shapes with a self-similarity. So the simplest fractal shape is this kind of a tree structure. So basically, every branch will split up into 2 branches or more branches, and every small branch will split out even further. So actually, it keeps going and it becomes a self-similar geometric shape. And actually, we can define a dimension, spatial dimension for this kind of a fractal geometry. It's not going to be an integer most of the time. So it's a pretty interesting and an exotic geometric shape. And because we have this kind of a tree example of the fractal, actually in many shapes in nature, we can actually define a fractal or fractional dimension. So some example I found online, so interesting example I found online is this one. So in this picture, there are 2 fractals. One is actually more well known, it's a broccoli. So broccoli has it's a classic example of a fractal shape in nature. And turns out there's another maybe a slightly less well-known example of fractal. It's actually just a beefsteak. So in this kind of beefsteak, you can see the fat distribution also have this kind of a branching structure. So if you Google online, actually you can find there are research papers studying the fractal dimension of beefsteak, and some papers even made a connection between the price of the steak and the fractal dimension of the fat distribution. Okay, if you're interested, you can look at those papers. And some other example, for example, human lung also have a fractal geometry because the bunkers also have this kind of branching geometry, branching structure. So there's also a fractal dimension, fractal self-similarity kind of fractal geometry in human lung as well. And also I found that this actually is something quite well studied, like using the fractal geometry and a fractal dimension to study how cancer affect the human lung. Okay, so under cancer, on a tumor growing, actually the human fractal dimension of a human lung actually can change. Actually, well, I didn't find any study about how COVID would change the human lung fractal dimension, but that's, I mean, that's something that maybe you can find out by yourself. Okay. Yeah. Okay. So let's get back to continuous matter systems. So it turns out that in continuous matter systems, the models which actually have a spontaneous fractal structure, in general, it's actually called something with subsystem symmetry. Okay, something with a subsystem symmetry. So fractal symmetry is actually a example of subsystem symmetry. So let me first review a little bit about the subsystem symmetry, and then we will get back to the fractal symmetry. So so in the early examples of the subsystem symmetry, this is one of the early examples of the subsystem symmetry. It actually was a model proposed by Paramikandi, Leon Balance, Matthew Fisher, my colleagues in Santa Barbara in 2002. Because actually I'm going to use this model quite often, especially in the second half of my talk. So I will just call this model as a PBF model. Okay, PBF model. So in the PBF model, they describe a boson, a hardcore boson, sorry, may not be hardcore, but the boson hopping on a square lattice. But actually, in addition to the standard Hubbard interaction of the boson, there's a ring exchange. There's a ring exchange. The ring exchange means that there's one boson hopping from this side to this side, and another boson hopping in the opposite direction from this side to this side. Sorry, can you see my cursor or not? Hello?
Yes.
Oh, okay. Okay, good. So this ring exchange actually conserves, you can see that it conserves the particle number on every line and also every column. So it means that this model actually conserves the particle number, the boson particle number along every line and also every column. So this model has a subsystem conservation or subsystem symmetry. So the motivation for them to study this model was to construct a 2+1 dimensional boson system, which actually is not a superfluid or Mott insulator. So we know that in 2+1 dimension, a simple boson system would tend to either condense the boson, which form a superfluid, or become a Mott insulator, which actually is gapped. Okay. But actually, this model, as they claim, so this model actually, the bosons do not condense and also not gapped. So they call this model a Bose metal. Okay, they call it they call this model a Bose metal. So in 2+1 dimension, actually, it's very rare for a boson not to condense and also not being gapped. Okay, so this model actually behaves a lot like a 1+1 dimensional model, 1+1 dimensional boson. So which means that there's no superfluid phase, there's no long range order of the boson creation operator, but actually there's an algebraic power law kind of decaying correlation of some other operator like the dipole operator. So I will get back to this later in the second half of my talk. Okay. So the bottom line is that because of this one-dimensional conserved or one-dimensional subsystem symmetry, this 2+1 dimensional model behaves a lot like a 1+1 dimensional model. So here's another example. It's an Ising version of the previous model, the Ising plaquette model. So still, it's a Ising degree of freedom defined on the square lattice, defined on the size of the square lattice. You sum over the plaquette term, and also there's a transverse field. There's a transfer field. So this model actually also has a one-dimensional subsystem symmetry. The product of a sigma x along each line and each column is actually conserved. They commute with the Hamiltonian. And this model behaves a lot like a one-dimensional quantum Ising model. For example, there's a self-duality at a 0 temperature. The self-duality actually exchange the K and H, So this actually means that suppose the system has a phase transition, the phase transition, if there's one phase transition, the phase transition will happen at H equals to K, okay, at H equals K. And the phase with K greater than H will have a spontaneous breaking of the subsystem symmetry. And when the H greater than K, the system is in a disordered phase without any spontaneous breaking of the subsystem symmetry. And also, just like the 1+1 dimensional quantum Ising model, so this model will have no classical phase transition at finite temperature. Okay, the subsystem symmetry breaking will actually be completely restored and become disordered by any infinitesimal thermal fluctuation. Okay, and also in 2+1 dimensional system, if you look at this model, this actually looks a lot like a Ising gauge theory. Okay, but this is not an Ising gauge theory because here the spins are defined on the vertices instead of the links of the square lattice. So this model does not have the Ising gauge theory. Ising gauge symmetry. It's just it only has the subsystem symmetry. Okay. Any questions so far?
No. Yes.
Okay. Yeah. Okay. So actually,
sorry. In that previous model, the spin is defined on the edges, not on the links. Defined on the corners of the the second example.
Yeah, they are the same. So this example is the same. The sigma, they are also defined on the side of the square lattice.
Okay. Thank you.
Yeah. So it's not a gauge theory, but still it has some weird subsystem symmetry. Right. Yeah. Okay. So in the last few years, actually, subsystem symmetry plus topological order. In general, the system is called a fracton topological order. So the fracton topological order has a type 1 and a type 2. So type 1 means that the subsystem symmetry or the conserved charges, they actually localized on the ordinary subset of the lattice, such like the one-dimensional line or the two-dimensional plane in the whole three-dimensional space. So there are many models, prototype models like this. This is Schaumann's model or X-cube model. There's also a type 2 model where the conserved charge, they actually own a fractal subset of the lattice, like the Haas code. Okay, like the Haas code. So it turns out that they are far more type 1 model than type 2 model. Okay, but actually, so in this talk, I will try to talk about a system which actually look a lot like the type 2 model. Okay, so I will reserve the type 1 model for the second half of my talk. And there are some review of fractons. So these are two review review papers on fractons. So if you are interested, I highly recommend you to read them. Okay, so I will talk about type 2 type of fractal symmetry. So actually the simple model, one of the simple model with the type 2 subsystem symmetry was proposed by Newman Moore. Actually that was like 12 years ago. And also Yoshida studied the model again in 2013. So it's actually a very simple model which look like this. Okay, this is called a Sierpinski triangle model. So let me show you what the model look like. It's actually sum over all the down-facing triangle of the triangular lattice. Okay, sum over only the down-facing triangle of the triangular lattice. And it's a product on every down-facing triangle. It's a product of the 3 spins on the 3 vertices of the down-facing triangle. Okay, 3 vertices of the down-facing triangle. So you can see that this model has an obvious ground state, which is that all spin equals to +1. Okay, all spin up is obviously a ground state. But you can also see that there are some other ground state. For example, every triangle I can have either all spin up or I can have a 2 spin down and 1 spin up. Okay, both are the ground state of the model. Okay, both are ground state of the model. So it turns out this model has a very large degeneracy of the excited state. So for example, this is one of the excited state. Okay, this is the one of the excited state. So if so all the other vertices have a spin equals to +1, but the spin on this Sierpinski triangle kind of a shape, fractal shape, have a spin equals to -1. Okay, the Sierpinski triangle is actually a fractal shape. It's actually a fractal shape. So if I flip the spin from up to down on the Sierpinski triangle, okay, then this is an excited state, but actually the energy cost for this excited state only cost at the 3 corners. Okay, only cost at the 3 corners of the triangle. The interior of the triangle does not cost any energy at all. Okay, so it means that I can separate the 3 corners as far as I can. Okay, I can separate them to very far distance. The excitation energy will still remain the same. Okay, will still remain the same. Okay, so there's a large number of degenerate excited states, and these excited states will have a fractal. We have a fractal geometry structure in it. Okay, so is this point clear? So you can check that every down-facing triangle in the middle either has all spin up or have 2 out of spin is a spin down. Okay, for example, this triangle has like a 2 down but a 1 up. This triangle also have 2 down but a 1 up. Okay, so it turns out that as long as you flip spin on the Sierpinski triangle, this will always be a ground. Sorry, well, will always not cost any energy. Okay.
May I say something?
Yeah, sure.
Because in this model and in the previous plaquette model, you didn't put any nearest neighbor interaction, and that somehow is what produces in the nearest neighbor interaction. What produces in the continuum limit produces a Laplacian. So you're writing an Hamiltonian that does not has ordinary waves, so without Laplacian, and so that produces this fancy. So I mean, on general grounds, it's really fine tuning the fact that you don't put any short range, any nearest neighbor interaction. It requires some fine tuning. It's not natural.
Yeah, it's so there is some fine tuning. So if you want to realize them in the real experimental system, certainly a lot of fine tuning is needed. This is why actually well, that's the point of the talk. I will try to propose experimental systems where I can construct these models with either very small fine tuning or no fine tuning at all.
Okay. There is another question from the audience. Sorry.
Yeah.
Is this theory, the triangular one, also not a gauge theory?
No, right. It's not a gauge theory at all. It's not a gauge theory.
Okay.
Yeah. Right. So the first question is very good. Actually, yeah. So the point of this talk is try to construct these models where this 3-spin or 4-spin interaction, they are the dominant energy scale. Although in ordinary condensed matter system, the 2-body interaction will dominate. So I will try to propose system where actually we can simulate this 3-body or 4-body interaction where they are the dominant energy scale, and all the other interaction, the nearest neighbor interaction, actually they become perturbations, which we can analyze using other methods. Okay. Okay, so yeah, okay, so let me first describe. I mean, so let's say we have this model constructed, and let's say that so what kind of properties this model have. So this model as a 2-dimensional statistical classical model, well, I mean, we can calculate a lot of things exactly using some exact method. This actually is not a very hard to calculate. So it turns out for this model, one can calculate the 3-spin correlation function. The 2-spin correlation will just be 0 at final temperature. But for 3-spin correlation function, Yoshida did the calculation. The calculation is the easiest to do in the dual picture, which actually I may be able to explain in a second. So the result is that actually the 3-spin correlation function will decay like this. It's like the exponential decay, but but actually it's faster than exponential because the power is log 3 over log 2. This is the dimension of the Sierpinski triangle. Okay, it's a spatial dimension of Sierpinski triangle. And actually, this three-point correlation is also only non-zero when the distance between the three spin actually satisfies this. Okay, 2 to the power m. Okay, 2 to the power m. But on the other hand, just like the one-dimensional Ising model, this model will be disordered by an infinitesimal temperature. Will be disordered by an infinitesimal temperature. Okay, so it means that this kind of fractal dimension also shows up by mirroring the correlation function at a finite temperature. Okay, and also actually suppose we consider suppose we look at what exact symmetry the system has for this model. So it turns out that suppose we define this model only with a periodic boundary condition, then actually with a certain system size, for example, with L equals to 2 to the power k minus 1, then this model does have a explicit symmetry. So this Hamiltonian with L equals to 2 to the power k minus 1, this Hamiltonian actually will commute with a operator. The operator is a product with is a product of sigma x on a Sierpinski triangle subset of the lattice. Okay, of the lattice. So this is actually is a explicit subsystem symmetry. It means the conserved charge is actually a product of certain operator on a subsystem of the entire lattice. So this actually means that suppose we don't know how to do RG for this model, but suppose we can. Okay, this fractal symmetry probably will prohibit the system from generating any two-body interaction, which violates this fractal symmetry. Okay, suppose the fractal. Okay, yeah. So actually, I suppose because the system has an explicit symmetry, then the RG should not generate any new term which violates this subsystem symmetry. But actually, honestly, we don't really know how to do RG for this model. At least not yet. Okay. Okay. So actually, in the last couple of years, there's another model which actually attracted a lot of attention, which is the quantum version of the Sierpinski triangle model. So we can make it quantum and study only the zero temperature phase diagram. So by making an Ising model quantum, we can just add a transverse field. Okay, this is a transverse field. So this quantum model actually now has a quantum fluctuation. We can just look at the ground state phase diagram of the quantum model. Okay, again, this quantum model, as I said before, has an explicit fractal subsystem symmetry, which is the product of sigma x on this on the Sierpinski triangle subset of the entire lattice. It commutes with the Hamiltonian. Okay, so this model has a lot of interesting features. So first of all, just like the 1+1 dimensional quantum Ising model, and also the 2+1 dimensional Placate model, which I mentioned before, this model is also self-dual. Okay, it's also self-dual. We can do the same kind of a duality transformation as the 1+1 dimensional quantum Ising model. There's a duality transformation which exchange the k term and h term. So that means the k term will become a transfer field term in the dual variable. The h term will become a 3-spin product term in the dual variable. So this also implies that it's likely that there's a one quantum phase transition at h equals to k. Okay, at h equals to k. Then suppose then actually okay. So this h equals to k phase transition separates two phases. When the k is greater than h, the model will spontaneously break the fractal symmetry, which I mentioned before, which actually is a fractal ordered phase. So the ground state will have a massive degeneracy, okay, because we can do a fractal subsystem transformation on the ground state. We will get a new ground state. So the ground state will not be invariant under the fractal symmetry transformation. So when k greater than h, it's actually a fractal ordered state. And then when k smaller than h, it's a disordered phase without any ground state degeneracy. Okay, without any ground state degeneracy. Then actually, the most interesting question will be the nature of the quantum phase transition at h equals to k. Okay, what's the nature of the quantum phase transition at h equals to k? So, well, I mean, as I said, I mean, so far we don't have a well-established field theory for spontaneous symmetry breaking or fractal symmetry yet. So we cannot do much analytical study for this quantum phase transition.
Yeah.
But,
You have a question?
yeah, sure, go ahead.
I'm sorry, just have a question. The previous slide said there's likely a phase transition.
Oh, yeah.
Can you clarify that point?
Yeah, right. There's a likely, so what I mean is that the self-duality will exchange K and H. So it means that suppose there's one phase transition, it will have to happen at H equals K, but in principle, there could be two phase transitions.
Okay.
And they just exchange. So
Okay,
this
thanks.
likely, actually, it means it's likely one transition, but there could be two transitions in principle. So is that clear? Oh.
Yes, yes. There are.
Okay, yeah. So numerically, actually, the people did find one quantum phase transition at h equals to k. Well, but still, I mean, the nature of the phase transition actually is still not very clear. So the slightly earlier studies suggest it's a first order transition in this paper, and a more recent work actually suggests a continuous phase transition. And what's even more interesting is that when they measure the correlation function of sigma x, for example, sigma x can be viewed as the energy density, for by the way. So the energy density correlation function actually decays as a power 1 over r to the power 2 delta, and delta equals to log 3 over log 2. So this was the conclusion in this more recent paper. So again, this is the spatial dimension of the Sierpinski triangle fractal shape. Okay, so suppose this is indeed a continuous phase transition. This actually, well, although actually I think numerical expert will have to look at this in more detail, more carefully, and actually really pin down the nature of the phase transition. But suppose it is a second order phase transition, it's actually going to be very interesting. We will have to develop a new field theory or RG analysis for this kind of phase transition and check whether these results are universal or not. There's a lot to do to develop a new paradigm to describe the fractal symmetry breaking kind of a phase transition. Okay, so the goal of this talk is to construct or simulate this model in real experimental system. And the platform I will try to use is what is called the Reedberg Atom. Okay, it's called a Reedberg Atom. So let me first review what is a Reedberg Atom. So Reedberg Atom is actually something which also attracted a lot of experimental efforts in the cold atom or atomic physics community. So Reedberg Atom is actually a very highly excited state of an atom, very highly excited state of atom. It behaves a lot like a hydrogen atom. You know, hydrogen atom is very simple. There's one proton in the center. There's an electron orbiting around it. But actually, it turns out that for many larger atoms, we can excite the atom to a state which actually is similar to the hydrogen atom. For example, for the potassium, okay, we can actually excite the external electron to a very high excited state with a very large principal quantum number, which means that there's a one electron which is very far away from the core of the atom, very far away from the core of the atom. And because of this, actually a lot of the features of the hydrogen atom can be used to simulate the highly excited atom, which is the Reedberg atom. For example, we know the energy level of the hydrogen atom goes like a minus E naught over n squared. This is the energy level of the hydrogen atom. So it turns out that for the Reedberg atom, the energy level is also very similar. It almost goes like a minus 1 over n squared, but there's a correction. The correction comes from the fact that the core of the atom is not a point. Okay, the proton is pretty much a point in the atom, but actually in the Reedberg atom, the core actually is a finite volume, although small, it's still a finite ball of electron density. So this actually will shift the energy level of the Reedberg atom a little bit. So actually it's not going to be precisely 1 over n squared. There's a correction. Okay, But actually, this atom still behaves like a hydrogen atom in many different ways. And another thing is that so in a hydrogen atom, we know that the size of the atom actually goes like an n squared. Okay, suppose I excite a electron to a high principal quantum number state. The radius of the electron orbit is actually going to be very big. It scales like n squared. So this means that Reedberg atoms can be very large. Okay, can be very large. So for two very large Reedberg atoms, they interact with each other through a pretty strong van der Waals potential. The van der Waals potential is actually come from the fluctuation of the dipole moment. Okay, come from the dipole moment. So for two objects with a permanent dipole moment, the dipole-dipole interaction will decay like a 1 over r cubed. But suppose we excite the electron to a state which is also at s orbital, then there's no permanent dipole moment. So the atom will interact with each other through a second order perturbation. Then the second order perturbation will give you 1 over r6 kind of van der Waals interaction. Okay, 1 over r to the power 6 van der Waals interaction. And also we can estimate the strength of the interaction. We can see that the coefficient of the van der Waals interaction will scale with the n to the power 11 of the principal quantum number. Okay, n to the power 11 of the principal quantum number. So for example, in Reedberg atom, actually people can excite the electron to the orbit with n equals to maybe 100 actually. Then actually the van der Waals interaction can be enormous. Okay, can be very, very large. Okay, so for two atoms nearby on the lattice, they have a very strong van der Waals interaction. But actually, because the 1 over r to 6, it means that interaction will decay very fast for the next neighbor. Okay, for the next neighbor. Okay, the nearest neighbor will have a very strong interaction, but the next neighbor can have a very weak interaction. So this means that this system actually is perfect for realizing some strongly interacting local Hamiltonian. Okay, first of all, it's a very strongly interacting atoms through van der Waals interaction. And second, the interaction can be quite local because the interaction decays very fast over the distance. Okay, so this actually is a part of a reason why Reedberg atoms have attracted a lot of attention in recent years to simulate condensed matter strongly correlated local Hamiltonians. So let me explain a bit more about Reedberg atoms. So basically, experimentally, how do we manipulate the Reedberg atoms? We can couple the atom to photons. Okay, to photons. The photon will have the frequency or the energy very close to the resonant frequency. The resonant frequency means the energy difference between the ground state and the Reedberg state. Okay, so the two atomic states have an energy difference. So actually, we can tune the photon energy very close to the energy difference between the Reedberg state and also the ground state of the atom. So then we can define a quantum number operator, n hat. Okay, n hat equals to 0 means that the system is at the ground state as the ground state of the atomic system, and n hat equals to 1. The system is such as the Reedberg state of the atom. Okay, the atom is at the Reedberg state. Okay. By the way, here the n hat means the number of the Reedberg atom is actually very different from the principal quantum number of the atom. Okay, so this n means the principal quantum number of the atom, and this n hat means the number operator of the Reedberg atom. They are very different things. I'm just running out of symbols. Okay, so in all the Reedberg atom simulation of condensed matter system, the Hamiltonian everybody start with is this one. Okay, is this one. The H equals to this. So the omega sigma x means that actually we can drive a resonating, a hopping or tunneling between the ground state and also the Reedberg state. We can drive a tunneling between n hat equals 0 and n hat equals to 1. This tunneling is called a Rabi oscillation, and this omega can be tuned experimentally. Depends on how strong you make the laser. Okay, depending on how strong you make the laser. So this omega can be tuned very easily experimentally. And then there's H naught. H naught actually is a term like this. So this V term is the van der Waals interaction between the Reedberg atoms. and there's a delta term which looks like a chemical potential, okay, of the Reedberg atom. Actually, this delta can be tuned through the detuning of the cavity QED techniques. Okay, so actually you don't have to know what detuning is, and I don't think I have time to explain that in detail. But actually, overall speaking, you can just think that in Reedberg atoms you can realize this kind of Hamiltonian. There's a transfer field kind of a term, just like the transfer field Ising model transfer field. There's a H naught having a interaction between the Reedberg atoms and also a chemical potential of the Reedberg atoms. So if you want to know more, about the Reedberg atoms, you can look at the review article. It's actually very good. Okay, this review article on the latest progress in the Reedberg atoms.
I have a question.
Yeah, sure.
Shouldn't one expect to have, because dipole interactions, you can have like hopping or spin flop between two atoms? You know what I mean?
Actually, well, I mean, so actually I think that's for the Reedberg atoms with dipole moment. For example, if I excite electron to a p orbital, so right now I'm talking about electron which excited to a Reedberg state, but it's still a s orbital. It's an s orbital state with a very large principal quantum number. If you excite the electron to a p orbital state, then actually indeed, as you said, there's like a super exchange kind of a term.
Yeah.
Yeah, right. So so that term is also written down in this review paper. So you can look at this review paper. So they discuss different kind of a Reedberg state. So for Reedberg state with only s orbital, then this is the most important term. But for a Reedberg state on the p orbital, actually in the next half of my talk, I will talk about some p orbital, but not the Reedberg p orbital. But anyway, so but when the Reedberg atom is on the p orbital, there's indeed some super exchange kind of term going on.
Okay, thanks.
Yeah, indeed. Actually, there's a very rich physics that one can explore in the Reedberg atoms. Okay, so let me first review what people have proposed with the Reedberg atoms. So recently there are two papers on realizing the Z2 topological order using the Reedberg atoms. So both are from the Harvard groups. Okay, both are from Harvard. So I will just illustrate what they propose in one of the two papers. So what they do is that they trap the atoms on a Kagome lattice, and we know the Kagome lattice is the dual of the triangular lattice, which means that the site of the Kagome lattice is the link of the triangular lattice. So the paper make use of the strong repulsion, between nearest neighbor, between neighboring Reedberg atoms. Okay, so actually they by tuning the parameter, they can realize a phase where on every hexagon there's only one Reedberg atoms, because the strong repulsion interaction actually does not like the system to have more than one Reedberg atoms on every hexagon. And then this model can be mapped to, then all the Reedberg atom configuration can be mapped to the configuration of the quantum diamond model on a triangular lattice. Okay, quantum diamond model on a triangular lattice. Okay, and we know very well that the quantum diamond model on the triangular lattice can be mapped to a Z2 gauge theory. And for the Z2 gauge theory, there's a Z2 topological order. Okay, there could be a Z2 topological order, depends on some other parameters, but there could be a Z2 topological order. Yeah, right. So basically, this probably is the first example of using the Reedberg atom to simulate some local Hamiltonian in quantum matter system, which will give us some non-trivial topological kind of order. Okay, some non-trivial, non-Landau kind of order. Okay. Yeah. So in this talk, I will try to use the Reedberg atom to simulate the Sierpinski triangle model. Okay, Sierpinski triangle model. So as was pointed out by one of the audience, of course, in a quantum matter system or in any real experimental system, simulating as a three-body term is going to be difficult, because the realistic interaction, just like the van der Waals interaction, actually only has a two-body interaction. So how do we actually simulate the three-body interaction through only two-body interaction? Okay. So let's try to do this. So let's consider a honeycomb lattice. Okay, I'm not sure whether you can see this. So there are some hexagons here, okay, honeycomb. So let's consider a honeycomb lattice. But actually the honeycomb lattice has an equivalent description as the decorated triangular lattice. Okay, so the site, the sublattice A of the honeycomb lattice actually is as the center of the down-facing triangle of the triangular lattice, and the sublattice B of the honeycomb lattice is as the vertex of the down-facing triangle, as the down-facing triangle of the triangular lattice. Okay, so we consider we trap atoms as on a honeycomb lattice, but equivalently we can also say that we trap atoms on both the vertices and also the center, and also the center of the down-facing triangles of the triangular lattice. Okay, so basically we will call the atoms on the vertices of the down-facing triangle as a target atom, and we will call the atoms as the center of the down-facing triangle as an auxiliary atom, And then we will choose the principal quantum number and principal quantum number for the target atom and the auxiliary atom as NB and NA, and we will choose them properly. Okay, but actually before we talk about that, let's say that we can tune the parameter of the system to realize this model, okay, to realize this Hamiltonian for the atoms. So this Hamiltonian, if you expand it, it only has two body interactions. It only has two body interactions. So this is the sum of all the down-facing triangles. Okay, the sum of all the down-facing triangles. So if you expand this term, you'll see that it involves the nearest neighbor interaction between the NA hat and NT hat. It means it involves a two-body interaction between the auxiliary atom as the center of the triangle and also the target atom as the vertex of triangle. It also involves the neighboring interaction between two target atoms, okay, between two target atoms, okay? So let's say we can realize this model first, and then later I will talk about how to realize it. So let's say we can realize the model first and see why this model can simulate the Sierpinski triangle three-spin model, okay, three body model. Okay, so let's look at the ground state of this Hamiltonian, okay, of this Hamiltonian. So to minimize this Hamiltonian, we want the square to be 0, okay, inside the square to be 0. So there are two ways to make the inside of square to be 0. One way is that NA equals to 1 and all the NT equals to 0. Okay, so the square will be 0. Another case is to make NA equal 0 and a 2 out of 3 NT is 1. Okay, 2 out of 3 NT equals to 1. So this actually can be one-to-one mapped to the ground state of the Sierpinski triangle model, which actually has a three-body interaction. So the state number 1, with actually all NT equals 0, is a map to all spin equals to up, okay, all spin up of the Sierpinski triangle. And actually the state with a 2 out of 3 NT equals to 1 is mapped to 2 out of 3 sigma z equals to -1, okay, equals to -1. So that means that the degenerate ground state of this Hamiltonian can be one-to-one mapped to the degenerate ground state of the Sierpinski triangle model with the three-body interaction, okay, through the mapping sigma equals to 1 minus 2n. Okay, is that clear? So these two models actually have the same ground states. Okay, in fact, the entire Hilbert space of the Sierpinski triangle model can be mapped to the states of the atom model, one-to-one mapped to states of the atom model. You can just do it carefully. It's a kind of tedious, but so I'm not going to go through it. But actually, I can show you. I mean, I can guarantee you that the 4 ground states of the Sierpinski triangle model is mapped to the 4 ground state of the atom model, atomic model, and the 4 excited states of the Sierpinski triangle model is mapped to the 4-fold degenerate excited states of the atomic model, like this. Okay. Of course, the atomic model has a larger Hilbert space. Okay, the atomic model has a larger Hilbert space, which means that actually we enlarge the Hilbert space so we can simulate the 3-body interaction with only 2-body interaction. So that means that there are some other states. Okay, there's some other state in the atomic Hilbert space, but actually this Hamiltonian will guarantee that all the other states, all the other extra states in the atomic Hamiltonian has an even larger energy. Okay, have even larger energy. So this means that we map the all the states of the Sierpinski triangle model to the low energy Hilbert space, to the low energy Hilbert space of the atomic system. Okay, of the atomic system. So is this clear, or is there a question?
Oh yeah, we have a question.
Okay, go ahead.
Okay, so does this mean that in the atomic model, the subsystem symmetry is only valid at low energies? And then
Yes, that's right. That's right. Yeah, I will get back to this later. I will get back to this later. Yeah.
Okay, thanks.
Sorry, I also have a question. So the fact that the extract states have a gap, which is, I think, is still V, so it's the same order as the separation between the grounds in the first excited state. Is that a problem?
This gap actually is this small v. This small v can be tuned. You know, there are two different parameters. Of course, actually, the most naturally they will be at the same order. Yeah, you are right. Most naturally they will be at the same order.
I see.
Yeah. So that means that indeed, most ideally, actually, I will just throw all these states away with the extreme energy gap. But actually, that's actually not going to be very easy to do experimentally. Yeah, so actually by saying low energy Hilbert space, I'm saying that there's a gap here and there's an energy gap which is small v. Okay, we can tune this v, but actually most likely in experimental system, I'm not going to tune this little v so much bigger than this big v. Yeah, but still, I will have a comment about this property later. Trust me, I'm also worried about this, but actually, so I will comment about this later.
Okay, thanks.
Yeah. Okay, so. Yeah. Okay. So yeah, right. So this is just an expansion of the Hamiltonian. You can see there's a two-body interaction between NA and NT. There's a two-body interaction between the two NTs. Okay. Yeah, right. So this is the realization of this model. So to realize this model, actually we can just tune the principal quantum number of the atom on stabilizer B, and also stabilizer A. We can choose some quantum number for them. Okay, to do that, we can just choose the right frequency of the photon of the laser that will be coupled the system to. So for so we choose potassium atom. We choose the potassium atom, and we can choose like an NB, the principal quantum number for NB for a target atom to be 113, and NA equals to some other number. So actually, the way we choose the number is through some numerical calculation of the energy level of the Reedberg atom. It's actually a very mature field, so we can actually have some algorithm to calculate them. Okay, so because the van der Waals interaction between Reedberg atoms, they decay fast enough with the distance, so there will be perturbations on top of this interaction. So this is only a nearest neighbor. This is only nearest neighbor, but there will be interaction on top of this interaction coming from the relatively longer range tail of the van der Waals interaction. But that interaction, because the van der Waals interaction decays fast enough with the distance, that interaction actually is not going to be very big. So for example, the next neighbor target atom interaction is about 4% of the nearest neighbor target atom interaction. And also the next neighbor target atom and the auxiliary atom interaction is also about 4% of the nearest neighbor interaction. Okay, so the interaction are there, but they are actually not going to be very big. So this means that suppose we try to probe fractal physics within a finite size, then actually all the fractal physics will still survive. But actually we cannot make the Sierpinski triangle extremely large. Okay, we cannot make the Sierpinski triangle extremely large. So the evaluation we did is that the Sierpinski triangle with the size up to L equals to 16 will still be the low energy excitation of the system. So when the Sierpinski triangle with a size bigger than 16, for example, next one will be 32. So the size 32 Sierpinski triangle will likely going to be fragmented into smaller Sierpinski triangle, but actually we can still simulate a Sierpinski triangle with a size up to L equals 16. Okay. Okay, so experimentally, what we can do to probe the fractal shape? Okay, what we can do to probe the fractal shape? So, for example, the cold atom system, actually, we can manipulate the cold atom system in actually a very precise way. We can actually manipulate each atom individually. Okay, we can manipulate each atom individually. So, for example, suppose I manipulate the Hamiltonian of the system at the 3 corners of a Sierpinski triangle, only at the 3 corners of a Sierpinski triangle. For example, I turn on the chemical potential for the Reedberg atom on the 3 corners. I turn on it slowly. I turn on a very slow manipulation of the 3 atom chemical potential. Then actually, if I do it slowly, there's an adiabatic theorem which guarantees that system will remain in a ground state as the instantaneous Hamiltonian. So it means that even if we only manipulate the 3 corners, we are supposed to see a emergence of a Sierpinski triangle kind of excitation in between. Okay, so this actually is something that we can directly probe or visualize the Sierpinski triangle in the cold atom system. And in a cold atom experiment, one can actually measure and probe every atom individually. So actually, we can easily map out this Sierpinski triangle structure. Okay, this is experimental proposal number 1. And number 2 is that we can also, so suppose I slowly manipulate the 3 atoms. Actually, we can create a Sierpinski triangle. But suppose I fast manipulate the parameters. If I fast manipulate them, I'm going to, I can actually probe the quantum dynamics. Okay, quantum dynamics, for example, if I quench the system, I actually change the Hamiltonian very fast. Then we can probe the quantum dynamics of the system. And also for system with for subsystem symmetry or even fractal symmetry, the quantum dynamics actually can be very interesting because actually these corners actually has a very low mobility. Okay, they are very immobile. Okay, as I said, the Sierpinski triangle excitation, the size of the triangle should be a 2 to the power n, which means that either the size will be 2, 4, 8, 16, which means that actually this vertex is very difficult for them to hop from 8 to 16. Okay, so actually they have a very constrained and very exotic dynamics, which can actually potentially be probed by the fast manipulation of the parameters in the system. Okay, so what else can we actually measure? For example, we can turn on the Rabi oscillation term. Okay, this is a Rabi oscillation term. As I said, actually we can drive the tunneling or transition between the ground state of the atom and the excited state of the atom and actually, just like the quantum Sierpinski triangle model, turning on this term can likely drive a quantum phase transition between the ordered phase, which had a spontaneous break, the fractal symmetry, and a disordered state, which actually restore the symmetry, Okay, so experimentally, one can measure the correlation function by taking the snapshot, by really taking a photo, of the configuration of the atoms. And by averaging many photos or snapshots, they can actually measure the quantum average or thermal average or thermal expression value of the correlation function. Okay, we can get the correlation function. Okay, but let me comment on the concerns that we have and also was raised by the audience, is that actually what we simulate is the so what we really want is a subset, is a low energy subset of the Hilbert space of the atomic system. But indeed, there will be some high energy states which may be involved as the quantum phase transition. Okay, Okay, so how do we deal with that? The answer is that actually we don't know how to deal with that theoretically because we don't have a well-established RG formalism. But those high energy states may or may not be involved in the low energy physics. Suppose the system has a continuum limit or thermodynamic limit, second order phase transition. Okay, so for example, suppose I have a U1 quantum phase transition, XY transition 2+1 dimension, which is a superfluid to model insular phase transition. And my Hilbert space, my UV system breaks the U1 symmetry down to Z4, or Zn with n greater than 4. We know that actually this anisotropy, this symmetry breaking is irrelevant. We know this symmetry breaking is irrelevant as the quantum phase transition, as the 3D XY quantum phase transition. So that symmetry breaking may not be important at all as the quantum phase transition. So here, actually, we don't know whether this UV breaking or the high energy states, which actually break the fractal symmetry, is going to be relevant or not as a quantum phase transition. Frankly, we don't even know whether this quantum phase transition is continuous or not. There's some numerical evidence show that it's continuous, but actually it's still an open question, I think. But I'm saying that actually this model at least simulate a quantum Sierpinski triangle model and a quantum phase transition with some perturbation. And actually the result of the measurement experimentally actually may help us develop a paradigm in the future which actually decides whether the perturbations are going to be relevant or irrelevant. Because actually normally when we do a quantum phase transition, we actually write down the most ideal case, then we analyze the perturbation through the RG scheme and determine whether the perturbation is relevant or irrelevant. Okay, so having this experimental realization can help us decide whether various kind of perturbations are relevant or not as the quantum phase transition, which can be studied in the future analytically. Okay. Yeah. So So by the way, actually, using the similar techniques, we can simulate many other models with fractal symmetry.
Okay.
So, for example, this is another model.
Cenke, sorry.
Yeah, go ahead.
Yeah, might this be a good point to take a short break, or can we take it soon? What do you think?
Sure. Yeah. Actually, let's see. Yeah, my second half of my talk is actually shorter. So I only have 2 slides left for the first half of my talk. So how about I finish the 2 slides, now I can give a shorter talk for the second half.
Yeah, that's perfect. Okay. Great.
Yeah, okay. So I'm saying that actually, so the whole trick in our realization, in the potential realization of the quantum Sierpinski triangle model is actually we sort of enlarge the Hilbert space, then we can simulate all the states of the fractal order in the low energy subset of the Hilbert space of a larger Hilbert space. Then we can simulate the 3-body interaction through a 2-body interaction. So we can do the same thing for other fractal kind of a model. Like this is the tetrahedron model. It's defined on a tetrahedron lattice. Actually, more precisely, it's a stacked triangular lattice. It's a stacked triangular lattice. So the sigma are defined on the vertex of the tetrahedron. But actually, when we try to simulate this model, we also decorate every tetrahedron with an extra atom. Then we can simulate this model through only 2-body interaction, which again can be engineered through the van der Waals interaction of the atoms. Okay, so we can do the same thing. We can simulate the 4-body interaction using 2-body interaction, and we realize the states as a low energy subset of the Hilbert space of the atomic system. Okay, but eventually the lattice will be a diamond lattice instead of a stacked triangular lattice. Okay, so this actually is pretty much this is the last slide of the part 1 of the talk. So basically, I want to say the quantum Sierpinski triangle model, although it's not fully understood, actually it actually calls for a new theoretical paradigm to study various interesting phenomena, various interesting properties of the fractal symmetry involved phase transition. And actually, we said that we can try to realize, at least to some finite size, the physics of the quantum Sierpinski triangle model, which has a 3-body interaction, but we can realize it through a Reedberg atom with only a 2-body interaction. And the platform of the Reedberg atom can actually allow us to directly probe the fractal structure, the correlation function, and also the quantum dynamics, of the system. Okay, so we can do this in codine experiments. And also, I want to acknowledge all the funding agencies for both my group and also my collaborator David Weld group. Okay, so that's the end of part 1. So I can take questions, or you can take a break. Yeah, it's up to the organizer.
Yes, if there are questions. Let's see. So let me ask a question. So this system, have they been already experimentally realized, or what you describe is a possibility but still has to be realized?
Well, I mean, certainly, okay. So realization of the fractal thing, actually, this certainly is very new and it's only a theoretical proposal. But actually, Reedberg Atom, people have used the Reedberg atoms to realize some to simulate some simpler quantum many-body system and the dynamics of the quantum many-body system, like the quantum Ising model and there's several other systems. Yeah, right. The advantage of this experiment system is that it's highly tunable, and actually we have like a single atom precision in principle. So actually many things can be done through this system. But actually so far, this specific proposal is just a proposal.
And so in particular, would it be possible, if it is realized, to settle the question whether there is a second order phase transition or not? Is it possible to measure correlation functions?
Yes,
kind of things?
Right. Yeah, so measure correlation function, you can do this. So actually, this is a standard way for measuring correlation function in cold atom system. It's like you do a lot of quantum measurements. You measure once, you get a number. You measure twice, then you average them. And actually, in cold atom system, you can measure many times. You can redo the experiment many times, and you measure the same thing many times and do the average. Yeah, so by doing that, actually you measure the correlation function, the average value, the expectation value of either the thermally average or quantum average of the correlation function.
I see. Thanks.
Yeah, right.
Okay, so I think we can take a 5 minutes break, and then we can continue with part 2.
Yeah.
Okay, so I think we can start with the second part, please.
Okay. Yeah. So actually, yeah. So the first half was about type 2, kind of subsystem symmetry. So the second half will be type 1. Yeah. Actually, well, I mean, this is the review of some pretty ancient things. Actually, yeah. This is something I did when I was a student. Yeah, with Matthew Fisher. Again, it's a platform of a cold atom, and we are going to try to realize some subsystem symmetry and also some fractal-like physics using the p-band cold atom. I will give a quick review of what a p-band cold atom is, and then I will talk about how to realize some of the interesting models that I mentioned at the beginning of the part 1 of my talk, like the Bose-Meadow phase, and also the quantum plaquette model with subsystem symmetry. How do we realize them using the p-band cold atom? And actually, then I will talk about the p-band cold atom in 3D, which actually have some many novel features. Yeah. Okay. So what is p-band atom? Okay. So basically, in cold atom system, actually, people can trap the atom in an optical lattice. So it's a lattice. It's an array of potentials. Array of potentials. So every potential is approximately a quadratic potential. And actually, from the basic quantum mechanics, we know that, well, I mean, we know how to solve the quadratic potential quantum mechanics problem. So ground state is a S wave. It's even under all the spatial reflection, inversion, and everything. The ground state is the S orbital, and the excited state is the P orbital. The first excited state is just has one node in the space, and it's odd under the spatial reflection. Okay. So actually, so notice that here we are talking about the wave function of the atom, not the wave function of the electron. So so in the second half of the talk, when I say the p-band atom, I mean that we literally pump the atom from the ground state to the p orbital of a single trap. Okay, the atom is actually at the p orbital of the Hilbert space of the single quadratic potential. Okay, so why do we actually why are people interested in the p-band cold atom? So first of all, the p orbital wave function extends longer along the x direction than along the y direction. Okay, extends longer along the x direction than the y direction. So so when the atom hops on the optical lattice, okay, so when the atom hops from one side to another side on the in the optical lattice, the p-band atom actually, for example, the px atom, which extends further along the x direction than along the y direction, the px orbital will hop stronger along the x direction than along the y direction. Okay, it will prefer to hop along the x direction than along the y direction. So in fact, one can try to solve some simple quantum mechanics problem and show that actually when the strength of the potential on every side is stronger and stronger, okay, actually the anisotropy is stronger and stronger. It means that the px orbital will hop much stronger along the x direction compared to the y direction. Okay, the ratio for the px to hop along x direction divided by the amplitude for the px orbital to hop along the y direction, this ratio will increase with the lattice potential. Okay, will increase with the lattice potential. So it means that in certain limit, the px orbital will only hop along the x direction, and the py orbital will only hop along the y direction, and the pz orbital will only hop along the z direction. Okay, will only hop along the z direction. So about 15 or 16 years ago, actually, the p-band cold atom has also attracted a lot of attention. It started with this paper. If you're interested, you can look at this paper. They did a lot of atomic physics analysis. Okay, started with this paper, and then later on attracted a lot of theoretical papers on the p-band cold atom. So the bottom line is the most important thing is that although the atoms are at the excited state of the optical lattice, they still have a quite long lifetime. Okay, the lifetime for the p-band cold atom actually is very long, which means that they can stay on the p-band and equilibrate on the p-band, form some many-body state of the p-band atom, and before they decay to other states. Okay, so this was evaluated in this model. Okay, this was evaluated in this model. So that means that many theoretical papers did assume that this p-band cold atom can stay on the p orbitals long enough to form some interesting many-body states before decaying to other states. And actually, there was a experiment which shows that the atoms on the p orbital can form a superfluid. Okay, can form a superfluid, which means that they can indeed equilibrate and form some many-body states before decaying to other states. Okay, before decaying to other states. Okay, so actually, as our work was actually start. So our work will start with the ideal limit that px orbital only hop along the x direction and py orbital only hop along the y direction, and then we turn on the interaction between them. Of course, this ideal limit will have perturbations. For example, there's still some small amount of hopping of the px orbital along the y direction and the py orbital along the x direction, and some other perturbations. So we will get to this kind of perturbations later. But let's first see what kind of interesting physics can happen when we assume this ideal limit, that px only hops along x direction and py only hops along the y direction. So this is the Hamiltonian we start with. Okay, the D is actually the operator for the p-band cold atom. Okay, so we can see that dx only hops along x direction, dy only hops along the y direction. And then there's a interaction, the Hubbard term, which can come from the S-wave scattering between all the atoms. Okay, between all the atoms. So let's actually assume we are considering a two-dimensional lattice, the two-dimensional lattice with a square lattice symmetry, which means that the px orbital and the py orbital, one extend along the x direction, one extend along the y direction, and they are degenerate. Okay, they are degenerate. So let's say that this u term is a dominant term in the Hamiltonian. Okay, this u term is a dominant term in the Hamiltonian. So when the u term dominates, it guarantees that total particle on every side is a constant. Okay, the total particle number, the px plus py particle number on every side is a constant. This means that actually it looks like there's not much dynamics one can have when I fix the particle number on every side, but turns out there's still some dynamics. For example, the px particle can hop along the x direction, and then because the particle number on this side will have to conserve, then the py particle will hop like this, and then which pushes the px particle to hop like this, and then push this py particle hop like this. Okay, so this is the ring exchange. Okay, there's a ring exchange. It means that this single term here, which fixes the particle number on every side, we actually make sure that the low energy dynamics will involve a ring exchange, which look like this. Okay, ring exchange of the px particles. So the ring exchange, if I write it in terms of the phase degree of freedom of the creation particle, of the creation and annihilation operator of the boson, we can always do this. Okay, we can write the creation or annihilation operator of a boson approximately as exponential I theta. Then this ring exchange can be written like this. Okay, this is the ring exchange. This is a ring exchange. Then now suppose I redefine theta x minus theta y equals to theta, and redefine nx minus ny, the particle number nx minus ny equals to, actually divided by 2 equals to n. Then now we can engineer a low energy effective Hamiltonian. Okay, we can engineer low energy effective Hamiltonian. And this Hamiltonian with the ring exchange is actually precisely the Bose-Metal phase, sorry, Bose-Metal model discussed by PBF, okay, PBF 2002. Okay, so this model has the one-dimensional subsystem symmetry. Okay, has the one-dimensional subsystem symmetry. Okay, so actually the low energy effective model for this system having one-dimensional subsystem symmetry actually is no surprise at all, because actually the px orbital indeed prefers to hop along the x direction, and py orbital indeed prefers to hop along the y direction. Okay, so what we did is just to mix them up using some interaction to guarantee that actually the hopping is mixed up. Okay, so px orbital is coordinated with the py orbital hopping. Okay, the px orbital hopping is coordinated with py orbital hopping, and eventually this two orbital problem reduced to a one orbital problem with subsystem symmetry. Okay, is that clear? Is there any question so far?
Yes, we have a question.
Yeah.
I'm sorry, just the small u, how is it defined?
Oh, small u. Okay, yeah. So yeah, this dot here, right? So actually, yeah, we assume this is the major interaction term. There are some small interaction term. So the small interaction term, actually, this u is just the nx minus ny square. If you plus these two terms together, you will get some interaction between nx, between ny, and some interspecies interaction between nx and ny with different amplitude.
Okay.
Yeah.
Thanks.
Yeah,
Okay.
there are no other questions.
Okay. Sorry, there's no other questions. I will proceed.
Yeah, sorry, I said there are no other questions for now. Yes.
Okay. Yeah, so I will analyze this model later. Okay, let me just first say that by mixing up the PSPY orbital, actually we can engineer this model, but I will do some analysis about this model later. Actually, there's another. Oh, sorry. Yeah, I can do analysis right now. So actually, so this model has a one-dimensional subsystem symmetry. Okay, this model has a one-dimensional subsystem symmetry. Actually, so we can actually do some naive analysis now. For example, we can expand the cosine term as the minimum. Okay, expand the cosine term as a minimum and turn this n square into partial tau theta square. So it means that suppose we ignore all the perturbations, this model will actually give you some dispersion which look like this. Okay, this is dispersion for this model. So this dispersion actually will have line nodes along the x-axis and the y-axis. So when ks equals 0, the dispersion will be 0. When ky equals 0, the dispersion will also be 0. So that means that suppose we look at this model, okay, this model will have larger infrared divergence than the ordinary 2+1 dimensional boson system. Okay, because the 2+1 dimensional boson system, actually the dispersion will only be 0 when ks, ky both become 0. But now, as long as one of them becomes 0, the dispersion will be 0. Okay, so it turns out this model has the feature that the bosons actually do not condense. Okay, the bosons actually do not condense. There's no long-range correlation. We can actually evaluate the correlation function between the boson. We can see that the correlation function is not a long range, but the system will remain gapless. The system will remain gapless. So this is what a Bose-Metal means. Okay, this is what a Bose-Metal means. Yeah. And actually, we can evaluate the boson correlation function. For example, actually the first non-trivial boson correlation function is actually the 4-point correlation function. Okay, it looks like this. The two-body correlation function will always vanish. There's too much infrared divergence. We have to drive it to be 0. But this kind of a 4-point correlation function will have this kind of exotic-looking exponential, but a minus double log, this kind of decay. Okay, exponential minus double log decay. And actually, this 4-point correlation function is only non-zero when the 4-point is at the 4 corners of the rectangle. Okay, it's at the 4 corners of the rectangle. This comes from the fact of the subsystem symmetry. Okay, so for example, if I annihilate one particle at here, I will have the creator particle along the same line. then I have to annihilate another particle at the same column and create another particle at the same line and column. So it means that these 4 points will have to locate at the 4 corners of a rectangle, yeah, to be non-zero. And the correlation function is neither long range nor short range, but have this kind of weird looking exponential minus double log. And also, just like the 1 + 1 dimensional boson, this algebraic phase actually is a self-dual. Okay, it's self-dual, and also has a dual Lagrangian, which look like this. Okay, this phi actually is like the dual boson of the 1 + 1 dimensional compact boson. And also the dual boson also have a non-trivial and also a similar 4-point correlation function, which look like this. Okay, so this model actually have a lot of properties like the 1 + 1 dimensional boson. Okay, is there any questions?
No.
Yeah. Okay, so actually, in the real world, there's some other perturbations which I actually did not discuss before. So actually, on every side, the symmetry will prohibit one px atom to transit into one py atom, but actually symmetry allows two px atom to convert into two py atom. Okay, one px will have a different parity from one py atom. So it means that one px atom cannot hop to one py atom, but two px atoms can hop into two py atom, because actually there's no longer any parity symmetry violation anymore. So this process can be described by this term, okay, by this term in the Hamiltonian. So it means that in reality, actually, we should add this term to the Hamiltonian. Okay, it will look like this. So when this term is very large, okay, actually it will break the U1 to Z2. Then this model will become the quantum placated model, which I mentioned before. Okay, this model will reduce the quantum placated model. The U1 will reduce Z2. Okay, will become the quantum placated model, which I mentioned before. This model, as I mentioned, have a lot of similar features of the one-dimensional quantum Ising model. It has the self-duality, which exchange K and H. Okay, and actually there's a quantum phase transition at H equals K, and many other things. Okay. Yeah, right. So now I do more analysis about this model. Okay, about this model. So actually we can compare this model with a one-dimensional compact boson. Okay, one-dimensional compact boson. For the one-dimensional compact boson or quantum rotor model, we know very well that this model has a gapless conformal field theory phase. Okay, with this kind of Lagrangian, and we can actually analyze. Instabilities of this model. For example, suppose I break the U1 symmetry to Zn symmetry, we turn on an operator like this. Okay, we turn on the operator like which break the U1 to Zn. And we can also turn on some other operators, vertex operators in the dual model, which look like this. Okay, then we can ask whether this gapless phase, this conformal field theory, is actually stable or unstable against these two perturbations. Okay, against these two perturbations. And the answer, well, we have a universal answer. Okay, we can just analyze the scaling dimension of these operators, and we can see that scaling dimension of this operator is a universal number times n squared. The scaling dimension of this operator is the universal number times n prime squared. Okay, so we can see that actually by tuning k, the Lagrangian parameter k, and also n and n prime, there's a finite window where this conformal field theory is going to be stable against these perturbations. Okay, against these perturbations. Okay, so we can actually ask whether the gapless phase I described before. By gapless phase, I mean that this phase. Okay, Okay, whether this phase with this weird decaying, okay, whether this gapless phase is stable against the perturbation or not. Okay, it's stable against the perturbation or not. Turns out that this question actually is a bit pain to answer. Okay, this question is a bit pain to answer. So actually, we can still try to analyze operators like this. We can try to turn on operator like this. For example, we talked about before that there's a pair conversion operator which actually hops two px particle to two py particle. Okay, it hops two px particle to two py particle. So this kind of operator actually is fairly certain. We are fairly certain that this kind of operator is irrelevant. Okay, we can do some analysis to show that this kind of operator is irrelevant. However, there could be some other operators which potentially can be relevant. Okay, for example, this operator. This is a dipole operator. This is a dipole operator. So this operator no longer is a cosine n gradient theta and a cosine n gradient phi. So these operators will break the subsystem symmetry. Okay, this operator will no longer conserve the particle number along one line or one column. Okay, it breaks the subsystem symmetry. So we can analyze whether this symmetry breaking is actually relevant or irrelevant as the gapless phase, as the both metal gapless phase in the 2+1 dimension. Okay, but turns out that the answer to this question is far less universal than the 1+1 dimensional compact boson. In the 1+1 dimensional compact boson, we know that these operators have a universal scaling dimension, so we don't have to worry about the UV details when we answer the question whether they are relevant or not. But it turns out analysis for these operators actually do depend on the UV details. Okay, so for example, this operator will have the suppose I take a mu equals to y. Okay, this is the y direction dipole operator. So it turns out that this operator will have a power law decay in the x tau plane. Okay, in the two-dimensional plane of the three-dimensional space. Okay, so so this operator will have a power law decay in the x plane and tau plane. Sorry, in the x tau plane. Okay, in the subsystem of the three-dimensional system. But the power of the correlation depends on the details of the lattice scale. Okay, depends on details of lattice scale. So it means this calculation, when we evaluate the correlation function of this operator will decay as a power law, but the power will have a cutoff coming in when we do calculations. And also the scaling dimension, okay, will also depend on what exactly we mean by this gradient theta. Okay, what exactly we mean by the gradient theta. So there are two ways to regularize this n gradient y theta on the lattice. One way is that it's just the n-fold of a dipole operator is n times the theta r minus y minus r theta is one way to regularize this operator. There's another way with the n gradient y theta is a theta r plus n times y minus r theta. Okay, there are two different ways. Turns out these two different scenarios also give us two different scaling dimensions. Okay, also give us two different scaling dimensions. Okay, so it means that to analyze whether these operators are relevant or not, it actually requires a lot of UV details. Depends on how we define these operators as the lattice scale. Okay, as a lattice scale. So actually, in the earliest PBF model, sorry, in the earliest PBF paper, actually they didn't really. I mean, they used the language of a scaling dimension, but actually to be sure of what they are doing, they actually literally did a perturbation theory of these operators. They did perturbation theory of these operators and see whether the higher order perturbation will dominate the lower order perturbation using in the IR or not. So if the higher order perturbation is stronger in the infrared limit than the lower order perturbation, then these operators are relevant by definition. Okay, so this actually is a tedious analysis, but they have to do that to be sure of whether these operators are relevant or not. Okay, so that's actually not a very easy question to answer. So the feature, so this peculiarity is actually called UV IR mixing in recent years. C for this recent paper on this subject. Okay, it just means that we cannot naively take the UV cutoff to infinity. Actually, there's a difference between taking a continuum limit and actually taking a thermodynamics limit. Okay, you can look at this paper to compare these two different definitions of the infrared physics. Okay, is there any question?
Yeah, sorry. And so along the x tau plane, these operators behave like a one-dimensional boson with some dimension of the operator. What about the y direction? What is the behavior?
Oh, the correlation along the y. So if these two dipole operators, they are not along the same. If they are not within the same x tau plane, actually the correlation will be zero.
Exactly zero?
Yeah, precisely zero. Because the reason is still again the subsystem symmetry. So we are evaluating the correlation function as the fixed point with the subsystem symmetry. So only the correlation function, which is invariant on the subsystem transformation, will be non-zero, right? So suppose this dipole operator, they are not within the same x tau plane, there will be some line without any particle number conservation. So it means that there will be some lines breaking the particle number conservation. So it means this correlation function will be zero. It's guaranteed by the subsystem symmetry of the fixed point.
I see. Okay, thanks.
Yeah, right. It's just like in the one-dimensional boson model. If we calculate the correlation function between two correlation operator, it's going to be zero because it breaks the U1 conservation of the system. Okay. So this actually is that another question?
No, it's okay. Thanks.
Okay. Okay. So right. So the subsystem symmetry actually poses a lot of challenge theoretically. Okay, poses a lot of challenge theoretically. So, but actually, we can actually design some three-dimensional version of this model and see that whether the subsystem symmetry will lead to a peculiarity in the 3 dimension as well. Turns out it does. Okay. So, for example, we can actually do the same analysis. Sorry, do the same construction in 3 dimension. We construct a 3-dimensional. We construct a 3-dimensional optical lattice with the px orbital, py orbital, and pz orbital on every side. And actually, we turn on a term here. We turn on a term which fixes the nx plus ny plus nz equals constant. Okay, ns plus nz plus ny plus nz equals a constant. Then again, at the low energy, we only allow the ring exchange, which I described before. Okay, there has to be some coordinated hopping between the px particle, py particle, pz particle to guarantee that every lattice side has the same, has a constant particle number. Then eventually we end up with this kind of a ring exchange model. Okay, we end up with this kind of a ring exchange model. So AB takes the value of x and y, and A and B do not equal to each other. Okay, so we have a partial x, partial y, theta x minus theta y, and a partial x, partial z, and a theta x minus theta z. Okay, so this is a 3-dimensional multi-flavor ring exchange model. So this model, suppose I diagonalize this model, I calculate the low energy dispersion, it will look like this. Okay, it has 2 non-zero dispersion. One dispersion, one mode, will have a line node, which means that when kx equals 0, ky equals 0, the dispersion will be 0. And another mode will have a plane mode, which means that as long as one of the 3 momentum being 0, the dispersion will be 0. Okay, you can look at this. So I have 2 modes. Okay, so this is the mode which will give us the most IR divergence when we do calculation, because this mode vanish at every plane. If we take kx equals 0, or ky equals 0, or kz equals 0, the dispersion will be 0. So this dispersion actually has the most IR divergence, will lead to most divergence in the calculation. Okay. So we can again do the duality transformation. So as we said, a 2-dimensional version of the ring exchange model is self-dual. The 3-dimensional model has a more interesting duality. Okay, we can run through the duality formalism either through the classical Steinbach problem. We can do the VLAN form and do the duality there, or we can do the quantum duality using the operators on the lattice. Okay, the dual of this multi-flavor ring exchange model, the dual actually is a loop model, and it's actually exotic loop model. Okay, so this actually, so if you look at this term, okay, for example, partial x phi y minus partial y phi x squared, this term looks like a magnetic field term of a U1 gauge field. But actually, in addition to that, there's one more partial in front of it, coming from the subsystem symmetry. Coming from the subsystem symmetry. For example, one of the terms will look like this. Okay, one of the terms here will look like this. It's like suppose you view this as a BZ. Okay, then this term is a partial Z BZ. Okay, the partial Z BZ. Okay, so actually on the lattice it will look like this: cosine partial Z BZ term. So this term will describe a loop hopping along the direction orthogonal to the loop. Okay, describes the loop hopping along the direction orthogonal to the loop. So if I just write down a lattice U1 gauge theory, it's again a loop model, but the U1 loop can hop anywhere. Okay, U1 loop can hop anywhere. Okay, but in this model, the U1 loop only hop along the direction orthogonal to the loop. Okay, so because of this, this model also have subsystem symmetry in addition to the ordinary gauge symmetry. Okay, this is the partial y, the partial alpha is the ordinary gauge transformation, but in addition to that, this model also has some subsystem symmetry like this. Okay, also has subsystem symmetry like this. Okay, so actually we can check the duality. We can check this model. This model will actually give us the same dispersion relation. Will give us the same dispersion relation as this. Okay, so also have two mode. I mean, the gauge theory always have the three plus one dimensional gauge theory also only has two physical mode. There's a longitudinal mode which is gapped, which is not physical. We know that, but they are two physical mode. So ordinary gauge theory will give us two transfer mode which are linear with momentum. But for this special gauge theory, it will give us two mode which look like this. Okay, two modes which look like this dispersion. Still have a line node and also plane node. Okay. Yeah. Again, we can study whether this model, the three-dimensional multi-flavor ring exchange model and the three-dimensional exotic loop model, whether they are stable against the subsystem symmetry breaking perturbation or not. So again, the question will involve the UV details. So for example, we can turn on operator like this. This is the ordinary electromagnetic field term, the cosine B term. So, so if we evaluate the correlation function of this term as this fixed point with both the U1 gauge symmetry and also the subsystem symmetry, the correlation function for this operator is non-zero and also power law in the tau z plane. It's also non-zero under power law at the tau z plane. But the decay power also depends on the UV details. Okay, so this model also has the subtlety of the UV IR mixing. So actually, when we do analysis, we have to carry the UV particle with us when we do calculation, and also we have to specify what kind of UV regulation we are using in this kind of a model. Okay, but potentially there could be a interesting exotic multi-flavor ring exchange or a exotic loop model gapless phase there with both the U1 gauge symmetry and also subsystem symmetry. Okay, any question?
No.
Okay, so so this is pretty much what I want to talk about in part 2. So basically, we covered that the p-band code atom. So I'm saying that by exciting atoms from the s orbital, which is the ground state of the optical lattice, to p-band, which is the excited state of the optical lattice, this atom can have a long lifetime, which means they can live there long enough to form some exotic states, some exotic strongly interacting states before decaying to other states. Okay, before decaying to other states in optical lattice. So the interacting p orbital atom can form exotic states of matter with subsystem symmetries in both the 2D and 3D optical lattice. And in both 2D and 3D optical lattice, actually, as a system can realize some algebraic both metal-like phases in both 2D and 3D. But the analysis for this state actually involves some subtlety, some UV subtlety in it. We have to be careful with what kind of a UV regulation we use in this analysis. Okay, so that's all I want to talk about. So this is actually a little bit old paper. Hope it's still interesting. Okay, so I will stop here and take questions.
Okay, thanks. Do we have questions? So let me ask you a question. So in the lattice models, in order to have the subsystem symmetry, you need to have some peculiar interactions that, in particular, if you try to go to the continuum limit, usually means that you have higher derivative interactions and you miss the standard, say, kinetic terms with two derivative interactions and so on. So is there something similar for the gauge theory that you mentioned at the end? Also, that yes. Gauge theory is some peculiar
right. So
action?
in principle, this term actually will exist. They may be small, but they will be there. So this is the dominant terms. So this is the model we start with. We due to this model, but this term in principle will still exist. So actually, this term breaks the subsystem symmetry. So that's why we have to evaluate whether it's relevant or irrelevant as the fixed point with the subsystem symmetry.
I see.
Yeah. So in principle, yeah, in principle, the terms which breaks the subsystem symmetry will be there. It's just that in these setups, these terms may be not so important, just in terms of pure magnitude, but still we need to analyze whether they're relevant or not. But if that turns out to be relevant and the magnitude is small, then the subsystem symmetry physics can still be observed up to a certain length scale, although maybe not exactly in the infrared limit.
Okay, and another question is in the, I mean, so suppose you realize an experimental realization of these systems, or at least you propose some way to do that. So it will be possible to choose the UV completion of these breaking terms. I mean, you said that there is this UV infrared mixing, and so depending on how you define the operator in the UV, you obtain different results. So would that be something which is experimentally controllable?
Definitely. Yeah, you can certainly design a UV model, especially in the cold atom system. You can do a lot of designing of the UV Hamiltonian. Yeah, I forgot what would be the most ideal or most optimal designing of the UV. That requires a lot of analysis. But actually it's possible. It's possible to design a very the optimal or the best UV model, actually make everything survive to the infrared limit. Yeah, but right now I probably don't have that most ideal UV design right now.
I see. Do we have more questions? Okay, no more questions from here. I guess from online as well. Okay, so thank you very much, Cenke, for the beautiful presentation.
Thank you.